during our PhD. We were like TAs together in, in an evolution course. And it's my pleasure to have you here teaching to my students, my kids. I call you my kids. You don't know, but you are. And it's a very, very big pleasure to have you here. And Paulinha, Paula Lemos Costa, Diogo Melo and Paula Lemos Costa. You can enter, guys. Paulinha, she was, she's a friend first, and then a colleague in 2 different laboratories. And I hope we think alike, but we think differently, and that's why you are here. Very important to have you here. But passing to the formal part, Diogo Melo is a molecular scientist by training, right? It's a different course here in University of São Paulo. And then he did his master and his PhD in genetics and evolution also here in University of São Paulo. Nowadays, he's a postdoc or a staff, I don't know how to call you, a researcher at University of Princeton University. And it's a pleasure to have you here. And mostly his interest in, how do I call that? In evolution and genetics and population genetics, and also micro and macroevolution. Paulinha is also a biologist by training, also or differently, I don't know. Biologist by training. She got her bachelor degree from Universidade de São Paulo and her master in ecology from Universidade de São Paulo, and then a PhD at Universidade Estadual de Campinas. Nowadays, she's a postdoc researcher at University of Chicago. Fancy people here, guys. And she's interested in many things related with biological diversity, and from intrapopulation variation to species formation, and how interactions affect the co-evolutionary dynamics between species. So it's a pleasure to have you here. Please help me to welcome these guys. And I think you are talking today, right? So Andrea is talking today. Have a good class.
Okay. Hi, everyone. Good morning. We're going to have today a short introduction, an introductory introduction to linear models, to simple linear models. This is a topic that you may have already seen in your undergrad courses, so it's not, our idea here is not to necessarily come back to a classic linear model course, but also help you understand in the context of statistical modeling, how we build models. So when we build models, we are dealing with predictor variables and with response variables. And when we do experiments, and we talked a little bit about this before, when you have an experiment, it's very clear the distinction with a variable that is the predictor and the variable that is the response, because you are measuring and you're manipulating the predictor variable, and you're measuring or you're observing the response variables. When we create statistical models, we have to make this distinction. If it's clear to you because it's an experiment, or if if you're building the model because you are confronted with a set of variables and you have to think about how to build your model. You are the one who is, when you build a model, you are establishing a hypothesis about the causation of the relationship. And the simplest way to do this is the linear model, the simple linear model. It uses only one predictor variable that we usually call x. I'm not saying anything new to you. And it has a direct effect on the response variable. And this is how our model will operate. It will operate under the understanding that this is true. This is not necessarily true, but this is how you build the model, and the model does what you say. A graphic representation of such a model is joining the predictor variables and the response variables with an arrow. We're going to be talking about this later. And as we have seen in the last couple of days, the response variable is being measured or is being observed, and it has a distribution. It can be modeled as random variables that we talked in the couple of days before. So linear regression assumes and operates under the assumption that this response variable has a normal distribution. So when we talk about all of this model building, this simple model building, the relationship, the linear relationship can be described by a line that has an intercept and a slope, and this is a simple way, it's the equation of a line. And these two statements are combined into the notation of this model. So when I said the response variable has a distribution, and we will assume that it has a normal distribution, this is the first line of this model. And the second states the effect that the response variable has on the predictor variable has on the response. I will be doing this, so don't let me do this mistake. The assumptions are, therefore, that the relationship is linear, the residuals are normally distributed, that the variation around the mean of y is random. It is not, it is not systematic. It's a sample that you took independently, so the variation is random. It's because it arises either from measurement or for variation that you did not take into account in your model. It also has the assumption of that variance is constant for all x values. If these assumptions are broken, you may need to think a little bit more about your model and to plot and to observe your data. We will be using a very simple data set. It has 9 points only. I will be talking about how to fit a linear regression with this sample data set. And the question is, of all the lines that could be built around this cloud of points, how do we choose the values of the parameters of the intercept and the slope that are best adjusted, that represent the relationship between x and y? And the simplest approach to do this is called ordinary least squares. You may most certainly heard of this, most probably already in your studies. And I will go slowly into ordinary least squares, and then we're going to jump. So for any possible line, any candidate line, imagine all these lines. Even if you have the perfect line, you can imagine like the one that you want. But in any case, the observed values of y, the points here in this graph, are going to be different from the predicted values. The predicted values lie in the line. But you seldom have, you basically never have measurements without variation. So you won't have data sets in which the points are totally aligned with any line, even the best line. So when we talk about residuals and what Paulo was talking about in the first class, when we talk about this variation, it will come from the variable itself, but also from the explanation, from the effect of the variable x. This is our definition of residuals. It's the difference between any observed data, and I will be using y subindex I. So for each point of y, of the observed data, we are going to be having differences with the estimates. And I will be using, for now, y hat. This little hat means the estimated by any line. And you could have, if you have different lines, You all the time have, like, all the lines state a set of estimated. But you want to find a good line where the residuals are minimum. And this is what ordinal least squares do. To do this calculation, it's quite simple. The magnitude, since the variation is random, you will have sometimes points that lie above a line and points that lie below the line. So we don't care about the absolute value of this difference. So the common practice is to square them. It will penalize more. It will add more importance to the deviations. And when we talk about the residual sum of squares, it's the total sum of these squared deviations to the line. I am painting here only one line, only the best line. But this calculation could be done for any candidate line. So you can have residual sum of squares of many lines, of many candidate lines, and some lines are evidently not good. Sometimes, for example, this line is evidently something that you are not going to think is a good candidate line. But if you calculate the residual sum of squares, you can have a number because you do have the prediction made by this line, and you will have huge residuals. That's why it's not a good line. Not only because the intuition when you see it is not, like, tells you that it's not a good line, but also the values of the residual sum of square are going to be huge. Ordinal least square minimizes from all the possibilities of combinations of the slopes and intercepts around your points. It minimizes this difference, this square difference. And there is some, like, the minimizing is a process that will end up, the solution for this minimization are the two parameters estimated by the regression line that are beta 1. I remember that I wrote beta 0 is the intercept and beta 1 is the slope, okay? So the solution for the slope is this one. So it will have to do with the variation in the x-axis. This variation of each point around the mean is the total sum, like it's how variable are the data in our response in a predictor variable. And the total variation of x is this. So this is what we call the total sum of squares. And we are going to be finding a solution in which the variation, the covariation, the word is not covariation, but the product of the variations, the effect of the x variable on the y variable is scaled by the variation along x. And to find the intercept, the solution is dependent on the fact that the mean values of both are part of the curve. They belong to the curve. So once you have the intercept, you can get easily the intercept because you have your y's, you have your x's, so you can take the mean values. So you could find beta 0. And we will do this later. So one important thing is that these values are estimates. In any setting, you will have a population. You will have a sample of the population. The points that I'm showing are a sample of a larger population. Or you will have data that comes from a sample of a large population. And the regression line that you get depends on the sampling that you have. So it's the best fit for the sample that you have at hand. Is it okay? If you had another sample, if you do repeated sample, if you do another experiment, if you were at another point in time where your measurement changes, you would have a slightly different regression line. And this is, they are not necessarily equal to the population regression. So this is something that I want you to have in mind for the following, because ordinal least squares gets to a point in which you have an answer about the value of your parameters, but this comes from a sample, and this has a variation around it, okay? And later we'll see, they will have distributions, okay? So as I was telling you before, when we talk about the whole variation in the setting of ordinal list of a linear model, the sum of squares of a variable is the amount of variation that the variable has around its mean. You can imagine a normal curve. We have the mean, we have mu, and we have some variation. This is the total variation of any variable, the sum of squares. When we talk about the response variable, the sum of squares of the response, the total variation that y shows in your data, does the same. It's showing the variation around the mean. You have a cloud of points. And when I talk about the sum, the variation in the axis, in the x-axis, you can picture a curve like, yes, there's an x-axis, and we have a mean, and there is some variation because I have different points in the x-axis, along the x-axis. But when you have a regression, as I showed you in the cloud of points, there's still variation around the mean. There is still some variation around the mean. So, and this is the total variation of this variable. What we want to understand is what amount, what part, what portion of this variation is caused by effects that we haven't been accounted for, that what we call the randomness of the variable, and what part of this variation is caused by the regression. Okay, so we were talking about errors, and we were talking about noise, and we were talking about residuals, and I would like to talk for now about unaccounted variation by the model, because you are the one who is deciding what predictor goes in this model. And it may be not the best predictor, but the fact that you're taking this decision means that you are deciding that the rest of the variation of the world, that you may understand that it can happen, you're not going to account for it. It does not mean that it's an error. We talk about errors colloquially. But at the end, the variation of a variable around its mean, the total sum of squares, is going to be caused in part under this model by the regression itself, by x, by variations in x, and this residual sum of squares, the variation that is left unaccounted. Okay, so when we talk about the sums of squares, this is it. Sums of squares of the regression. This can take different names depending on the author, the source, and the residual sum of squares that can be also called in different ways. So I want to, like, are we okay with this? This is okay, so perfect. So yes, that's what I was saying. We want to understand how much of this variation comes from which of the sources. Imagine that the variation was only unaccounted, that actually x does not do anything does not do anything to y. What we would have is unaccounted variation only operating on your curve. And this is what happens when you have a cloud of points that has, like, sometimes it's very easy to see it graphically, sometimes it's not. But imagine that the whole variation was accounted for by x, by the variation. And this is the case where all the lines or your data would be aligned on top of the regression line. But we are talking about random variables, so we know this is not going to happen. So between these two extremes, between the fact that the regression explains everything, that is inherently impossible because we are dealing with random variables, and the explanation and the possibility that x does not do anything, has nothing to do with x, we have a continuum of proportions, if you want to say. Yes? Are we okay with that? And this is why we do this variation partition. When we talk about partition of the variation, it's about this that we're talking about.
Yeah, so you said that there is the variation that is explained by the regression, and there is a portion of the variation that is not accounted by the regression, which is just random variation. And now you mentioned that I know it's an hypothetical case, but there's also a case that my variation in X can explain the variation I observe.
The variation?
I'm not sure if my question makes any sense.
No. You can.
No, yeah, because you mentioned that there is a variation of the variable X, right?
Mm-hmm.
And that could explain the variation that you observed in your data.
Mm-hmm.
Also, there's the regression that you calculated. That explains some of the variation.
This is the explanation.
Oh, okay.
Like what your model is doing is saying my hypothesis here is that variation in X causes variation in Y.
Oh, okay.
So when we talk about variation in X, like when we say that X causes a variation, we're talking about the model, we're talking about the regression.
Okay, yeah, so I was thinking of something else.
Okay. What I am also saying is that the estimates, the points that are on top of the line are estimates by the model. And depending on how good is the fit of the model, of your data, you can have points that are very close to the line and the residuals are very tiny, or you can have a cloud of points that where residuals are higher also. But there's not going to be a moment in most of data sets that where the measurements are so precise that you have everyone on top of the regression data. Does anyone want to say anything, ask anything? Okay. This is a graphic representation of what we're talking about. Okay, so this should be. Okay, now it fits. When we talk about the variation, this is the same data set and the same data set that we were plotting before. When you talk about the variation in Y, you have a mean of the values and you have a deviation from the values that you're observing from this mean. And this is what we're talking about when we write. I should have. Sorry, Roberto. When we talk about, but I was just going to do this, like X, Y, X. I keep doing this. Okay, this is this first graph here. You can change this, yes, maybe, okay. This is the calculation for the total sum of squares, and this is variation of Y. And when we have a regression line, what we do, the residuals of this variation, is what was left unexplained by it, unaccounted for by it. Okay, so this is our RSS, our residual sum of squares. Yes, this was unaccounted for. So the explanation, the effect, a measure of the effect of X on Y is the difference between the variation that has the total variation that comes from any source, and the variation that you left unaccounted for. Okay, you can do an experiment with your minds. Imagine a regression that has no effect of like a setting where you don't have this nice relationship. You have curves that are less, that can have like different values for the residuals. And they might look more as the intercept model, as the model made without effect. We want to understand which part of this variation is accounted by X. And this could be done. We have a thing with scales. We can have different scales in the axis, and sometimes we cannot fully understand if we only calculate sums of squares, because depending on the scales, this can take in values that are in the scales of the variables that you're measuring. So we need a way to standardize this proportion of variation that is explained by the model. And this is what we call the coefficient of determination. So what we are doing here is that we are saying that the sums of squares of the regression is equal to the sum of squares of the value of the variable. Maybe I am short, so maybe you're not watching this, minus the residual sum of squares. And what the coefficient of determination does is it looks for the proportion of the explanation done by the regression as a proportion of the whole variation, which part of the variation, which proportion is. So this value lies into between 0 and 1. Either it explains very few, or it explains a lot. And all the variation, the case in 1 would be because all the variation is due to regression. It will measure how close to the regressions, how well is the goodness of fit of the model. So it's not a confirmation of causality. It can hint you that the model is good, but it's not like you have to come back to the setting where you built your model. And you can say, okay, there is a relation, I can infer a relation, but this does not mean by any means that you have causation. This is something that you can be using a variable to explain that actually does not have a direct effect, that is operating via other variables, even if your model looks very good, because that's what you told your model to do. Okay? And this variation partition, these differences between the whole amount of variation in X and the residual, the sum of squares, is key to understanding some of the summaries when we do linear models, and this is something that we'll do soon. You have tables that look like this. Yes. So what you will have is the sources of variation. This is a summary of the sources of variation. In summary tables, what you have is the source by each predictor. Yes, and what it means, the sum of squares is this. We have already talked, and the residuals are the variation that is unaccounted. So the total variation is the sum of squares. The unaccounted variation is the residual sum of squares, and these are the values. When we see in classic summaries of ANOVAs, of linear models, we see F ratios. And F ratios are basically a measure of how large is the explanation of the regression compared to the explanation unaccounted for. Okay? And F is one of the distributions, it's a random variable. It was discovered by frequentist statisticians, and this is the classic way of doing linear models. And what it does is that it compares this number that you're having in your data set with an F distribution with a certain number of degrees of freedom. Okay, so this is it.
I already asked the professor once, but I wanted you to explain the whole process of this model, and then the p-value just comes with the test, right? With the test of significance, or is it from the? Because this is the summary of my model when I do it in R, right?
It looks something like this. It's a modified version, but yes, and in any statistical software.
But like, yeah, from what I understood these last days, the p-value is a value that I get with a significance test, and it is not part of the model itself. And then I wanted you to like explain the whole process of like, because we have to assume normality of my dependent variable. No, of the residuals, of the results. But then, yeah, I just wanted you to like just explain that, because when I learned a bit of statistics at my undergrad studies, the difference between test and model and distribution was shown in like a different way, and I already kind of asked that, but I guess it's not just me that has that doubt.
Okay. So what we said that like this is a statistical test. This is comparing the sources of variation of your model with a theoretical distribution. So the F distribution. So a p-value is usually used. We are not going to be talking a lot about significance in this course, but a p-value. Why does it have to be small?
I know that.
Okay.
It's like the p-value it comes from the significance test.
It comes from your distribution, your F distribution. It comes from tables, theoretical tables. If this F ratio, your proportion that you obtained, is large, it means that your predictor variable explained a lot. But the fact that this comes from statistical curves, it's a comparison with another distribution. So I was not going to dwell on this, but it's only an adjustment. It's only an adjustment compared to theoretical curves. Do you? What we're going to do is make the whole process in R, like the calculations, for you to grasp this. But we are not going to dwell on the p-values and the significances of the tests. Because this is not something that we want to emphasize. The p-value is the possibility that you may be accepted results when the null hypothesis is null. We're not going to talk about statistical like hypothesis testing.
But that is a different thing from the model.
That's not a different thing from the model, but in the frequentist approach, it's being compared with distributions. We can come back to this in the code, okay? And to the lab, like you, please.
Can you go back one slide, please?
Yes.
I understood the sum of squares and how we got r squared, and how it tells us about if our linear regression makes sense. But I'm sorry, I just don't know what df is,
Okay.
nor f ratio.
Sure. So DF stands for degrees of freedom.
Okay.
DF is a way to understand how much independent variable information you have when you do your calculations. So it depends on the amount of data that you have, that is n, and it depends on the number of parameters that you are having to calculate. So when you divide, for example, when you take this means of squares, you cannot assume that you have the whole data independent to the calculation. The degrees of freedom will penalize this value because you already used some of the information when you feed the line. So it's a way to penalize, and it's a way to understand how small your, if you have a very small data set, you won't have enough. The mean squares are going to be divided by a large number. So it will correct a little bit these explanations. Degrees of freedom are one of the least intuitive topics, but they are penalizing the size of your sample and the amount of parameters that you're having. Does anyone want to say anything? Does anyone want to comment? Are we going to be using, this is not going to be part. Tomorrow when we talk about multiple regression, we will come back to this because this is the simple model I was going to show you, something about data simulation. And tomorrow we can come back to these summaries. So this is how a regression linear simple model looks like in R. And it will give you the estimates for the parameters. It will give you beta 0, what we have been calling beta 0. It's going to be the intercept of the model. And it's going to give you the slope. And in more complex models, it will give you the parameters for each one of the variables. Yes. This standard error is corrected. It's not the RSS. The RSS goes through standardization. So you won't have exactly the same values. And you will have these proportions and this comparison with theoretical curves that we can show later. And we will have how significant the model is. Since betas are having variation, we also can calculate confidence intervals for these values and understand if they are different from 0 or not. And we have some calculation about this is related to RSS. It's residual. It has been standardized by the sample amount. And we have some adjustments for the R square, for the coefficient of determination. But this comparison is with the theoretical curve of F. I will maybe plot an example. So the example data set that we have been using, that I have been using in these slides, is this. And I would like you to use it so we can come back and do it by hand to explore this data set. So if I gave you this data set, we go to the lab and we can check this model, okay? The only thing is, to do the example, I didn't I didn't pick variables with my hand. I didn't choose random or arbitrary variables to do this data set. This didn't come out of my mind. How I created this data set was by using this notation of the model. So these are simulated data, and we can generate the data. And the way we generate it, I hope it helps you understand this notation and how the data set is going to be born about from distributions. So you can open your sessions. We're going to go to the lab. So you have an RStudio session and you have a project. So check that your upper corner says it has the name of the project, so R knows where you are. I will just leave this for a while until you open the R session, and we go to the initial part of the lab. When you're done.
Summary.
Se você quer,
Não, eu queria só dar uma olhadinha nela.
você tem no nosso site.
Ah,
Está no
verdade.
site.
Não, sim, mas então, eu ia perguntar quantos aqui os valores, então, na verdade, eu poderia ter um limite, né? Se tivesse uma regressão, todos os pontos em cima da regressão, isso ia, tipo, por exemplo, meu F seria 1.
Isso, exato. So are we okay with this? So I would like to join you in this simulation, in this tiny simulation. Before we continue, I will just open my R2. I will open the project that we did yesterday. And I will be working in R like you are. Like I won't have a pre-done script, but the information is in our page. In the lab, in the link for the lab. So I will create, and I recommend you to do that, a second script, because we changed topics a little bit, because it's more clear. And we have this you can go to the this is not the one. You can go to the link for the lab and go from here. What I mean is that I can do, like, if you have any questions about how this data was created, if you want any explanation, extra explanation. Okay. So you can read, and then in something like 5 minutes, I will go through the code, or like you can ask anything, only about the data set and how it was generated, okay? So you have 5 minutes to look at the code and to see if you understand how it relates to the notation and to check, okay? We have already a table of values, so you can see if you are going to have, when at the end of this tiny chunk of code, if you have the data set, if you have the same data set that I was showing to you, okay? So in 5 minutes, I am like open to questions about this simulation. Pode.
Você tem F muito alto, isso quer dizer que a variação desses pontos em torno dessa reta é menor do que a variação em relação à média total.
É que toda a proporção da variação.
E tem uma variação de cada ponto.
A quantidade de variações possível valor do eleitor. Vocês vão ver depois. Tem uma avaliação. Então, o que a análise balizada dá é, em vez de botar valores pontuais, isso é um ponto assim, eles acham, não, o que faz lógica, o que faz então, isso é um bem fazer. Mas na hora não foi com ela, que você está fazendo uma questão de conhecer um pouquinho das pessoas, talvez não essa questão de minutos, programas, então você queria pensar qual que seria mais esses são quadrados de qual que seria a média? Qual que é a média? A média não precisa ser 50, se você altura as pessoas. Então, então você começa a fazer a partir de parâmetros. Não precisa fazer assim. Você monta um modelo. Que funciona, esses valores. Isso que eu quero falar.
Nunca vai obter, a gente só pega a nota.
Mas que eu valor esperado.
Sim, tá.
Afinal, você não vai obter, mas você tem o valor mais importante, porque a equação da você não obtém.
Da regressão?
Sim. O que eu estou criando com literal? É literal.
É verdade. É a minha
Então,
regressão.
mesmo que você não tenha, fica. O dado foi criado com ele na base.
Isso a gente fica no momento do zero. Tem aqui minha base de dados que eu coletei. Então, a minha regressão disso, eu saí das perguntas na altura e o peso das pessoas, botei, calculei minha regressão. Essa regressão é minha, isso que é a minha regressão que é a partir da minha amostra, e existe uma regressão da população.
So it's okay.
Summary the values of B, F, etc. This regression with it.
This is only a calculation that you did. It's not yet a model. You're not fitting a model. You're just checking that what you calculated is correct. So you can go further in the tutorial to see a little bit more. This for now is only a line. So I said 5 minutes, but if you want a couple more, or if you have questions, we are taking questions. I want to check that you understood why this data exists and how we built it. Okay. Was it clear to you all? Do I? Falar. Como?
Não, você está falando comigo?
Sim, sim.
Não, só fala para eles que tem tá pressuposto um sigma, na sua simulação está pressuposto um sigma de constante. Né?
Sim.
Eles perguntaram, não, tá, talvez eu não sei se tivesse obtido para fim didático.
So, in this example, some values are taken arbitrarily. This was not a data set that was meant to model any particular process, but when you have other kinds of models, you will have to think about possible distributions and possible values for some parameters. So in this case, there are some arbitrary values that I chose to just do this plot. The first is the x values. The x values are taken uniformly from a sequence. Yes. They could also be drawn from a distribution. They could have a mean and variation around their means. So only for didactic purposes, they are arbitrary. And the values that I chose for beta 0 and beta 1 are also arbitrary. This was to create the regression. But what is interesting is that the whole variation in the data was created from a random normal variable that takes our line equation, our regression equation, as the mean expected value, as mu, and has a variation around its mean. So this is how we get synthetic points. Okay. And the values, this is the value. So the values are accounting for variation. With this distribution, it has me that has a curve, a curve equation, arbitrary. Yes, so beta 0 is equal to 1.2. Beta 1 is equal to 3 plus 5. And the whole data set is created by taking random samples out of it. So this is how we will be specifying the models and the values. And the data set that is created at the end, if you want to come back. Has x, has me, the estimated value, and it has the values. And the residuals for this data would be each value, each yi obtained, minus mu, that is the expected value that responds to a linear equation. Are we okay with this? Diogo, Inacio, if you have any comments. But the next step is we're going to calculate. You? Please. Were you going to say something? Okay. You did like. Do you have mine? Okay. You already
if you were working with a real data set, we should delete the last dot because he looks like an outlier. And what kind of consequence we're going to face if we keep outliers on our linear regression.
Why do you say it's an outlier?
Oh.
So this is something that can be tested in diagnostic points. So if to you now it looks like an outlier, it does not mean that it is. If you order your data, and the fact that you created them from a random variable makes it very hard. It could be an outlier in some sense, but also it's part of the distribution. So this is something that was created by you. So in this case, we have diagnostic plots. I can show you after we do the model. But also dealing with these outliers is very tricky. And sometimes what statistical methods sometimes say, this is an outlier, this is a point that is having tons of influence in your data. The decision of removing everything is not necessarily always the good decision. So this is only for now. This is going to be after we do the model. I will show you the diagnostic plots, but only by looking at like this, you cannot say it's an outlier. You shouldn't, okay? At least you have to order the data. Check how it's distributed.
So I think I understood what we got in the end, that the red line is different from the blue line because the red line was generated from the random points that we created using a normal distribution from the data set, right? But my question, I guess, is if the random points were generated from a normal distribution, is the linear regression the best method to obtain the line, to obtain our approximation? Is it the best?
It goes on backwards because you already, it's not only the best, it's the way you did it. So since we are simulating the data, we're creating it. Some of the questions regarding, sometimes we're used to deal with the data and then ask about the model. And in this moment, we know for sure that we generated the data from a random distribution. And even when we see this, we see that variation is different. If you take out the seed, did you see the first line is set seed? Set seed is a random number generation. It allows you to have the same data set, everyone. But if you took it out, you could have still a data set that you know that it comes from a linear distribution, that the best model, like the expected model to describe this relationship is linear. But the fact that there is variation, that you created variation, that you inserted variation. So this question comes from another part of the thought experiment, because you know that already. You could use other models, other kinds of analysis, but you know it stems out from a regression. So it's not exactly the order of the thought experiment. So remember, we know where this data come from. You can play with the values of standard deviation, and with n, of course. This is what's going to show you for the slides, to see how a regression can be created. But this, we can do it later. Like, you can have lots of points, and if you have standard deviation that is high, the variation will be high, because it's going to the data are going to spread around, and in consequence, when you do the model, when you see the model, you expect that the R squared is going to be large, because you put a lot of variation into it. So you have the control right now of the parameters and of the amount of variation around the mean that you have, only for this toy example. Any comments? Paulo?
No, just a small comment that I think it's a good point to stress that we will use simulated data a lot in this course. Do you have an idea why we are doing this?
Probably because most of biological data doesn't have a normal distribution, and then with simulated, you can just use a normal distribution.
Can you repeat? I am the one who didn't hear.
Because most of biological data doesn't have a normal distribution, so it's easy to just simulate something with that, and then we can use it.
Yeah, sure. We are simulating this case data that come from a normal distribution that has its expected value as a linear relationship to other variable. So in this case, we are using normal, but in a more general tone, what we want is to simulate a situation which never happens, that you know the truth. So a very, very important thing here is that when you try to fit the model, you are trying to estimate the parameters of this model from data. And this data came from some process that we, in this case, we hypothesize that this data come from a normal process that generates many other data if you go to the field and collect more, for example. So the idea here is to create a situation when you know the truth, so you can compare how the model performs comparing to the truth. In real world, you don't have this opportunity in general. So that's the idea. So the red line, right?
Yes.
Is the truth.
Yes.
So you can see that this estimation of parameters gives you something that it's close to truth, right? So the model is working as we would like it. It works, but still you have some degree of error or uncertainty. Is the red line, which is the
This is with beta hat. So they calculated beta hat, beta 0 and 1.
The true beta.
From the OLS.
The true beta.
The true is the one that we defined. We defined this as the linear. So we have the true, and it's the blue, and it's this one.
Okay, so it's the blue line.
Yes, yes.
Okay, sorry. So
yeah, it's the other way around.
That's why.
But
so
yes. But yes, and
just
even
this comment on simulating data.
Yes, exactly. No, this is something. This is why we are stopping a little bit here. Even if we're talking about linear models, because this is something that we will be doing along the course, that we know the process that generated the data. And this allows us to understand what is happening. And we understand that even when we control part of the variation, there's part of the variation that comes from life, from the fact that random variables exist and that variation exists. Are we cool with this? In the notation, I omitted the fact that there's a sigma, there's a parameter extra, and this notation should have sigma. So I have this distribution. And the equation for the first parameter for mu is the linear equation, but in this case, sigma would be a constant, which is another one of the assumptions of a linear model. But in other modeling settings, you could have sigmas that also have their own distributions. Okay? So you calculate the coefficients and you go on. I don't know if you already have the summaries of the linear model and you're checking. So this is how you fit the linear model. And we check the intercept. I didn't know how was going to be the time, how the time was going to be. But we have some following steps after we do this model that can help us understand how good the model is. We can check the summaries, and this is something that I would like you to do right now. So I will just add it to our script. So I will just execute like you guys, like you all. You have the, oh, that's it. You have the formulas. The same way that you did the calculation for beta hat and beta 1 hat, you have in the slides, you have the formulas for the sum of squares of y and the residual sum of squares. So using these formulas, the next step would be to do this calculation. Okay, so do this. Based on the calculations. I will put the formulas in the tutorial as we speak. But do you understand what I am saying? We have this. Wait. We have RSS for this model, and this is the formula. So please do calculate RSS for our model while I add this part of the tutorial. I'm sorry, I will be doing this. What? Okay. Sorry. I wasn't able to do this. Here. Okay, so I will let you with this. The next step is to calculate RSS, and then you go to the slides and calculate the sum of squares of y and the sum of squares of the regression, okay? Oi.
cima da média da amostra, da média dos números simulados, não foi? Tá vendo que o Y tá com... Ah, não, aqui não.
Tá igualzinho.
Mas aqui, ó, também, aqui tá com 16 e 12. Não tá exatamente.
Não tá a mesma coisa, não. Então, peraí.
Eu acho que não.
Ah, pode ser...
Tá dando um número muito pequenininho, o RSS.
Está faltando um parêntese. É uma soma de quadrados. Não é uma soma ao quadrado.
Ai, tá.
Ah,
So, estava quer dizer, tranquilo. Já passei por aí. Tá? So, hey. So we are going to finish in 4 minutes. No, I don't want to interrupt you. But I need to say it. 12 e-mails. Era entender também o processo de simulação dos dados. Isso. Então, vai ter coisas extra, que são tipo mais clássicas da regressão, que eu vou falar agora. Hey everyone. Ok, sim, porque tem coisas assim, a parte do summary e a parte de fazer uma linear é meio tranquilo de fazer, né? Então, eu vou adicionar ao tutorial. Vocês podem fazer qualquer coisa amanhã. Vai passar para o demora. Então, não vamos parar muito aqui, assim, a ideia é já que vem do T velho, é um que eu vou falar. O T tem uma, assim, dá para... O T faz parte dessas proporções também. Passa pela extensão, passa por essa extensão, também tenta a normalidade. Mas o que basicamente está acontecendo aqui nessa conversa é, por exemplo, uma proporção de não sei quanto que intercepta, quanto que explicado por aí, quanto que experiência justa. Então, o que vale é uma standardização, uma padronização dessa proporção. Daí você vai para a decide o é bem mais condensado do que a a decisão do que mostrar uma standardizada é ligeiramente diferente. Você não quer tirar RSS, você vai parar e para obter esse standard error, você tem que dividir pela raiz para tem um passinho a mais, porque senão a gente tem que parar os limites. Mas eu vou deixar depois explorar com calma.
A pergunta sobre mais ou menos por onde julga um valor de que seja